And we're going to take a look at the key for exam 1 from 2014 for Chem 351. So in exam 1, first question is about nomenclature. A structure from the name or the name from the structure is required. You may choose either systematic or common names. So for this first one, root word is cyclobutane. Right, so a 4-member ring. 1 bromo, 2 ethyl, so 2 carbon piece. It doesn't, the 1 and 2 doesn't matter here. That's worth 2 points. Dimethyl ether. Ether, when we had an oxygen with 2 carbons bonded to it. In this case, dimethyl, so 2 methyls. This structure here, we would have to have probably found the parent chain, find the longest chain, and that's 5 carbons. And we had noticed what's off it, so the 5 carbon, that's pentane, and there is a methyl off that, so actually this should be a methyl there, an M there for methyl. So 3-methylpentane. Here again, the structure is drawn for us. We find the longest parent chain. In this case, we want to include the oxygen, the hydroxyl had to be in that parent chain. We like to give OH priority, so we say it's an octanol. Right? 1, 2, 3, 4, 5, 6, 7, 8. Octanol. There's a methyl group on the 4th carbon, so 4-methyl-octanol, all meaning OH. This one, we had a 7-membered ring, so that's the parent chain. So a cycloheptane, 7-membered ring, heptane, cyclo, and 2 methyls, 1,2-dimethyl cycloheptane. Next part, it said, draw the molecule below in a Newman projection. Be sure to translate the spatial arrangement correctly in the direction and follow direction. So in this case, you really had to notice that this was wedged and this was hatched. Right, this Newman projection was pre-made for you. So the N was coming out at you. So if you rotated this way, the nitrogen would be on your right, the H would be on your left if you're looking down 1 to 2. And the tert-butyl group, this 4-carbon piece, would be up there to the top. Now if you go to carbon 2, OH is on the same side as NH2, so those would be right there. The chlorine is down, so the chlorine's there, that's H is there. Now we want you to rotate clockwise, carbon 1 clockwise, 60 degrees. And so everything in the back stays the same. The OH, the H, and the Cl don't move. Just rotate the first one. Now from a staggered conformation, go to an eclipse. So the tert-butyl is on top of the OH. The NH2 is on top of the chlorine. The 2 H's are eclipsing. Rotate another 60 degrees counterclockwise. We're back to a staggered conformation. In this case, the 4-carbon piece, tert-butyl as we call it, is between the OH and the Cl. The NH2 is there, and then the H's are there. So we had to rotate around there to see that. So circle the lowest energy Newman projection, explain your reasoning. And this one's kind of showing good reasoning about sterics. Essentially, you knew the lowest energy, you knew the eclipse one was completely out of the question. So it had to be one of the 2 staggereds. And the question then becomes, we want to get all the big stuff away from each other. So we circle this top one because we're saying NH2 is smaller than these 4 carbon groups, right? There's 3 hydrogens on each one of these carbons, so 9 hydrogens hang out here. So if we're going to be staggered, we'd rather have the smallest groups possible there. So it's better to have a small group here than this large group with all those hydrogens. So that's the way we went with that. So here the first question, number 3 here, it says, draw the structures below in a cyclohexane ring uses wedges and hatches. So you're given a chair structure, obviously shown wedges and hatches, and they're asking you to take this chair structure and actually make it a cyclohexane ring. One thing you should notice, the bromine and this methyl are both pointed up, right? Or at least they're both on the same side, right? We assume this is up, we just kind of that, so they're both be wedged. Or you could assume this side was down, but they're both on the same side. You notice that the bromine and this methyl are both on the same side, so they could be wedged or hatched, but they both have to be on the same side. Next part here says draw the molecule below in a chair conformation. So now we're taking a cyclohexane, a flat structure with wedges and hatches, and turning it into a chair structure. Again, the methyl and the chlorine are obviously on opposite sides. Remember, opposite side, the actual side of the ring, whether it's on top or bottom, is not directly related to axial or equatorial, right? You can be axial and be up, you can be equatorial and be pointed up, or you can be axial and down and equatorial and pointed down, right? This is the relative spatial arrangement. So one of the ways you could have drawn it, the chlorine is pointed down, I think the wedge is pointed down. And if that's the case, as you go over, this methyl must be up, and if it's going to be up in this position, it must be axial up. Right, it must be axial up if I start adding in. So there's an axial up there, There'd be an axial down there, equatorial up, axial down there, equatorial down there. Right? So the chlorine and the methyl here, right, these are all H's. The chlorine and the methyl here must be on opposite sides. Another way you could draw it, instead of the chlorine being equatorial, you could have the chlorine being axial. And if that's the case, the methyl in this case would be equatorial, but it's up. Notice how the chlorine's down in both cases, and the methyl's up in both cases. But as you do a ring flip, right, what was axial becomes equatorial, but it always stays up. What was equatorial becomes axial, but in this case it always stays down. And you can do this a couple other ways as well. Draw the condensed structure from the formula below. The tough part about this is recognizing that this carbon right here is bonded to that OH, and then this carbon is bonded to that carbon and has a ketone, carbonyl. You see that CO like that. And then a CH3, right, this carbon had 3 CH3s bound to it. That's the tricky part with that. Which compound in each pair is more acidic? Explain why. So again, we're looking at acidity, so we're talking about, when we say just acid, we're probably talking about bonds to hydrogen, right? So electron deficiency. And these are reactions, so we're trying to think about polar bonds to hydrogen. So either the bond itself is polar, right? So the reactive starting materials, or the product we make is stabilized, right? So if reaction takes place, one of two things: stable products and or reactive starting materials. So in this case, you could talk about resonance of the product. So if I show, right, this has a resonance structure that this sulfur one does not, so the conjugate base of a negative charge, we can do resonance. You also go think about induction, because this oxygen could be pulling, right? Either answer is okay. Make sure you circle it. Again, with the nitrogen and the phosphorus, the difference between nitrogen and phosphorus is size, right? Nitrogen is smaller than phosphorus, so an NH bond versus a pH bond. Phosphorus is big; it's going to be have larger, less orbital overlap with hydrogen. Therefore, it's going to be a more reactive bond. So that's the key. Here we're comparing this CH bond to this CH bond, sp2 to sp3. Key here is hybridization. An sp2 orbital is closer to the nucleus, so it will stabilize a lone pair better because it's closer to the nucleus and opposites attract. Last one is 2 carboxylic acids. So the difference here is this one has 3 fluorines, right? And that's induction, pulling away electron density, weakening this OH bond, making it more reactive, right? And it's pulling away electron density to weaken that bond. All right, moving on to question 7 here. It says, for the example below, indicate the hybridization state of the indicated atom. For this, the question, of course, is always how many pi bonds are we bonded to? So in this case, this oxygen is bonded to 1 pi bond, so it's sp2 hybrid state, right? Hybrid state. This carbon right here has no pi bond, so it's sp3. That carbon right there has 2 pi bonds, so it's sp. Right, carbon right there, 1 pi bond, sp2. Nitrogen, no pi bonds, sp3. Right, and again, hybrid states are associated with hybrid orbitals, right? P orbitals are the only type of orbitals that make pi bonds. So in a case if you're sp hybridized, you have 2 pi bonds. That means you need to have 2 p orbitals, and everybody else is mixed up. And sp2 has 1 pi bond, so 1 p orbital, and what's left over is 3 sp2s to form the sigma bonds. And then sp3, of course, has no pi bond, so then it ends up with 4 sp3 orbitals. Very good. So let's look on to the next one. So now we're talking about boiling points. Predict which compound in each pair will have the higher boiling point, and give a short answer why. Give a short answer why. So here we have water versus methanol. Right, water is capable of doing more H bonding. Right, there's 2 OHs versus 1, so it's kind of a higher boiling point, a stronger intermolecular force. Here are carboxylic acid versus acetone. Right, again H bonding and more polar bonds. Right, so H bonding more polar bonds there. Bromoethane versus iodoethane, more polarizable. Right, iodine I is such a large thing with so many electron orbitals. It's more polarizable. It's kind of a squishy ball. So it's going to create more of a dipole-dipole interaction. And then here, a straight chain butane versus a butane that's more branched. This would have stronger van der Waals interaction, more stacking. So it's going to have a higher boiling point for that. Here's your acid-base question. Indicate the products in the following acid-base reaction. Explain how you determine which is an acid or a base. And then draw curved arrows to show the electron flow in the reaction. So the first one, indicate the products. So you first had to recognize that this nitrogen, right, its lone pair is going to be more reactive because it's less electronegative, right, than oxygen. Plus this is a polar OH bond, right? An OH bond is always going to be more polar than a NH bond, so the nitrogen is the base, right? So that means the nitrogen is getting a hydrogen, and this O is losing a hydrogen. So the electrons flow and attack, right? We always start arrows at electron density, attack the hydrogen. The OH bond electrons move to get a new lone pair in the oxygen. The nitrogen itself lost a lone pair because that new lone pair is forming this new NH bond. And there you go. Alright, the last page here, number 10, says rank the overall dipole moment from smallest to largest. So again, we're looking here for polar covalent bonds. And not just polar covalent bonds, but also the three-dimensional structure of them and how that relates. So the first one here you should recognize, we'll see carbon-fluorine. Fluorine's super electronegative, but you gotta be careful here because there's 4 fluorines. So all these fluorines are gonna pull equally in all directions. It's kind of like that cheerleader model. And so you're gonna get no dipole, so that's 1. And then from there you look and say, well, I have OH, OH, 2 OHs, 2 Fs, 2 nitrogens. I would probably guess the fluorines are going to pull the most, or most electronegative, so that's 4. And then oxygen versus nitrogen, I would say oxygen is more electronegative, so it's more polar covalent bonds, so that would be 3, and then this would be 2. Next part here, it says which of these pairs of molecules ought to dissolve in each other, and explain your reasoning, right? This comes back to like dissolves like. And if you're polar and covalent, if you're a polar organic solvent, I'm polar organic solvent, they would dissolve each other. So in this case, you have an ether, actually diether, and a diamine, right? So they both have polar covalent bonds, both have similar numbers of carbons, they both should dissolve each other. Here we have diethyl ether and a salt, right, and an ionic bond. They shouldn't dissolve in each other, right? The salt would dissolve in water, but it's probably not going to dissolve in diethyl ether, right? An ionic bond, right? Like dissolves like, this has charges, this does not. Briefly explain why I- is less reactive base than F-, right? Again, I- is this big squishy thing. It has these a lot of electrons, a lot of orbitals that can spread that charge out, and electron making it less reactive, right? If you can spread the charge out, be it resonance or just being large, that makes you less reactive, whereas F- is super small, it's going to be super reactive. Those lone pairs are going to want to react. They're not going to sit there. Predict which compound the pair will have a higher will have to be higher in energy, and give a short answer on why. So this comes back to these two: a 5-member ring versus a 3-member ring. Angle strain. So a triangle has 180 degrees in a triangle. The bond angles here would have to be 60 degrees, and those are all sp3 hybridized carbons, so no pi bonds. And they want to be 109.5, so it's going to be really a lot of angle strain, and it's going to be an unhappy molecule. It's not going to sit there very happily. The next one, you have 2 chair structures, and this is asking about diaxial interactions. When things are axial, they're much closer to each other, right? If they're on the same side of the ring, they're both down in this case. These 2 axial methyls are seeing each other, and they don't like that, right? Bonds want to be away from each other, versus here where one of the methyls is down and one's up, and one's axial and one's equatorial, so they're not seeing each other. So that 1, 2, 3 diaxial interactions, things want to be away from each other. Things would rather not be axial, especially diaxial. And the final question is a bonus question about cis-decline and transdecline. Draw them in the chair conformation. So if you look here, cis means the 2 H's are on the same side. Trans means 1 H is up and 1 H is down. And you had to draw these 2 chair structures to get that. Pretty difficult to do. Here's the cis. You can see the cis. And here you can see the H's are trans. Right here, H is down axial, H is down equatorial, H is down axial, H is up. So even though in this case, even though the H's are axial, it's better to have the H's axial than in this case to have the actual carbon here going axial, right? H is much smaller than a carbon. So even though these H's are axial, things are obviously more spread out here. So the trans is actually lower in energy because it avoids those diaxial interactions.